Hi everyone, I want to talk to you today about this idea that I'm gonna call scaled units. Especially we're going to be scaling length units. But we'll talk a little bit about why it's length units in a little bit. But let's suppose for a minute we want to compare objects of the same type. So we have a uniformly charged rod. What is the electric field that this uniformly charged rod creates, and how does that compare with the electric field created by a non-uniformly charged rod, where say we have more positive charges up here and down here and less over here. We can also compare objects of different types. Say, for example, a rod and a hoop, or a disc, or whatever. There are lots of options. Okay. So the simplest way that we can think about the electric field is we can think about the electric field as it's always going to be the Coulomb constant times the charge of the object over the size of the object squared. And so this electric field should always be proportional to this, and we'll talk about this idea in a second with a specific example of the rod, starting on the next slide. So suppose we have a rod with a uniform charge density. That's just the charge of the rod divided by the length of the rod. And we're interested in what the electric field is at some point a distance x away from the center of the rod. Well, on Thursday, we basically solved this problem. It is kq over x squared plus L squared. And you can see for a minute that this is a mixture of physical constants, the Coulomb constant K. It's a mixture of properties of the rod, Q and L, as well as properties of where you are looking in space, the distance x. And so it would be nice if we could separate this into an expression that had just the physical constant, the charge of the rod, and the length of the rod squared, all times something that depends on x. This is our goal. Let's do a little bit of algebraic gymnastics to do this. So let's just start by pulling this term out. This term kq over L squared out. So we can do that. Kq over L squared. This means that we now have times x squared plus L squared over L squared. All I've done is insert an L squared over L squared and pull these terms out. I can now group these terms. I can factor out an L squared from the square root and use that to cancel one of these L squareds, and I should get x over L squared plus 1. So now I just have this strange combination x over L. So normally when we think about our x, we think about it as a distance in meters. But for this problem, the meter isn't necessarily convenient. It's just an arbitrary length that somebody decided a long time ago. It's the distance between two scratch marks on a bar in Paris, France. So let's just pick a different length unit. we're going to pick a new length unit, and that's going to be L, the distance of the rod. So I'm going to make a new length x prime, which is just x over L, and that's just a new way of measuring length. So when I make this substitution, my electric field is kq over L squared. This only depends on the charge of the object and the size of the object and the physical constant k, which is what we wanted to, was our goal up here. And this is times x prime squared plus 1. And this depends on where you are. And so in this way, we can separate this kind of scaling factor from this. And it turns out that anytime I use a rod, I'll have this sort of term in front, and this will depend on how the charge is distributed. Let's do a concrete example of this. Now let's look at the same rod, except we're going to be looking around about the end instead of. So before we had our rod and we were looking at distance x this way down from the center. Now let's look at distance x away from the edge, and we can do the calculation. I believe it's in your book. You can find the electric field is kq over x times x plus L. And remember, our goal was to get something that had kq over L squared times something that depends on x. Some sort of function of x over L, like we had before. Okay, so let's do that. Let's pull out kq over L squared, x plus L over L squared. I'll put one of these L's with this x and one of these L's in this term in parentheses, and we'll get kq over L squared, x over L, x over L plus 1. And we've got our goal again when we replace these guys with x prime. So we can see then that EX will be kq over L squared, x prime plus 1. Whereas, remember about the other direction, this term in this second term was 1 over x prime squared plus 1 square root. So you can see that this function will have a different behavior than this function, and that's why, and it makes sense that the field should change differently along this direction than it changes along this direction. But we can see that here, and we don't need to worry about the individual properties of the rod. In our class today, so in class on Tuesday, we're going to be exploring two different kinds of charged objects, a disk and a hoop. And a disk is a solid object. It's just a circle. It'll have some radius r, and we'll have some charge q spread out somehow throughout the entire circle bit of the object, and the hoop is just a very thin ring. So the chart, and again, this will have a radius r. We are not going to worry about the thickness. Will be not important. Won't be important, but we'll have the charge spread out just along the length of the hoop. So again, this distance r and the charge q that we're putting onto these objects will be what are going into both of these. And so for this, we're going to be looking at kq over r squared as our sort of basic unit of electric field, and we're going to want to see what fractions of that are going on here. Pop quiz. What kind of charge density should we use for this? Is this a lambda, a sigma, or a rho? And what about for this? Is this a lambda, a sigma, or a rho? Bring your answers to class. We'll see you on Tuesday.